Okay, we're going to look at deriving the moment of inertia of a rod about its center. Okay, and for all of these, the process is pretty much going to be the same. We're going to start with the moment of inertia of a tiny chunk of matter and add all those chunks together. Okay, so in the case of a rod rotating about its center, what we would choose, here I'm going to do a side view of this rod as well. But makes sense, you know, we're talking about a very thin rod here, a rod that essentially only has the dimension of length to it. So the choice of our dm for this would be pretty easy. It's just going to be a tiny chunk of this rod that has mass dm, and that's at some position r. Okay, and like we will do with all of these as well, we're going to take advantage of the fact that this is of uniform density. And this time we're talking linear density, so we use lambda, which is the ratio. It has uniform mass to length. Okay, and so that is to say that that is the density of our little chunk too. And if you remember, this is how we're going to get eventually get our integral into something that we can actually integrate. Okay, so to find the moment of inertia of this or anything, we're going to say, okay, let's figure out what the moment of inertia of our tiny chunk is. Its di is equal to dm r squared. And if we want to find the moment of inertia of the entire rod, that's going to be summing together those di's. And so then we need to therefore sum together these. Okay, so the sum of our di's is the moment of inertia of our rod. And typically we see this written as r squared dm. And that's from, in this case, what's tricky about this is the bounds of our integral, working from our rotational axis over here, we're going to go from this point in our rod over to here. That's going to be the bounds of our integral. So it would really, if you think about it, it's going to be negative L over 2, half a length in the negative direction to L over 2, half a length in the positive direction. Okay, if we evaluated this from 0 to L, that would be like putting the rotational axis at one end, which is not, that's another question, but that's not what we're looking at here. Okay, so we've got the bounds of our integral, we've got the basics of it set up. The only thing that we need to do now is bring together what we know from the density over into here. Okay, so using this density relationship, I'm going to say that dm is equal to density dr. Okay, and I could leave it at that, or you could say, think about it, that's equal to m over L dr. And that would be useful because m, we're saying the mass of the entire rod, L, the length of the entire rod, those are both constants. Okay, you could do it either way. Eventually, we're going to take advantage of that though. All right, so I'm going to say, moving on with my integral here, it's from negative L over 2 to L over 2. And bringing in for dm, we're going to have r squared times lambda dr. Okay, and the importance of that, if you remember, is now we've got agreement here. We've got something that we can integrate. Okay, so let's do just that. All right, starting the rest of this it's pretty much just calculus from this point. Lambda density is a constant, so we're going to pull that out of our integral. Let's rewrite it one more time before we get going. Negative L over 2 to L over 2 of r squared dr. Okay, lambda on the outside. Okay, so evaluating this integral then, we get lambda of r cubed over 3 from L over 2 negative L over 2 to L over 2. And we're going to say we get L over 2 cubed over 3 minus negative L over 2 cubed over 3. Okay, and that negative matters, of course. Okay, all of this times our density. All right, and now it's just a matter of cleaning this up to get our best result, or our simplest result possible. So L cubed over 3, or sorry, L cubed, distributing that cubed, we're going to get L cubed over 8 over 3 minus a negative, so we could go right to calling this a plus, L cubed over 8 over 3 times lambda. All right, and so really what this is going to be is L cubed over 24 plus L cubed over 24, which reduces to L cubed over, I guess that would be 2/24 or 1/12. So lambda times L cubed over 12. Okay, and you could stop right there, but like we tend to like to do, because the density is constant and that has M and L in it, let's substitute in for that, or you could have done that from the beginning. I just didn't want to write as much, so I didn't do that. So as a final step, we can say density is M over L times L cubed over 12. And now what we get is that one of these L's go away. And that's a good check for moment of inertia. We should always have a mass quantity times some kind of length quantity squared. And we get, you can pull out a 1/12 out front, 1/12 ml squared. Okay, it's only for a rod, and it's a rod about its center.